We're going to talk about ions, what it means to break up into ions. And we know that there are two major types of substances that we talked about when we did naming. We talked about having ionic compounds, which were made of metals and nonmetals, and then we also talked about a different type of compound. What were they called? It starts with an M. Molecular. Perfect. And the molecular compounds are not made of metals and nonmetals. They're made of just two what? Nonmetals. Perfect. So the nonmetals, when they bond, they actually will share their electrons. So it's not an exchange of electrons, it's just a sharing of the electrons. And when they share the electrons, there is no real charge difference. There could be a slight charge difference where one of the atoms could be pulling on the electrons more and have the electrons surrounding themselves more than the other one. And we call that a partial negative charge or a partial positive charge on the one that it doesn't have the electrons spending as much time. Well, the thing with ionic compounds is one of the atoms will actually strip the other one of its electron, okay? And it has so much of a want, basically, for this electron, and so it'll take the electron away, leaving one of them without missing one or two or maybe three or maybe four or maybe 5 or 6 electrons. If they lose electrons, then we say that the charge is what? Positive. Losing negative makes it positive. The one that gains electrons becomes negative. Okay, we've heard a word, electricity, and what stem of words that we're talking about right now is the same? What's inside of there? Elect. We're talking about the movement of electrons. Okay, in order to get electricity to flow, you can basically get a movement of electrons, and so if you have charge, then you can get that to happen. I simply have a beaker of water. Okay, that's all I have here is a beaker of water. I have a light bulb. And so here I just have a couple of electrodes, and what I'm going to do is, and you can electrocute yourself with this, so I'm going to make sure that I don't touch the tip of this once I get it plugged in. Because once I get it plugged in, what's going to start flowing? Perfect. Electrons. So I want to make sure that the electricity, as that's flowing, if I were to touch this, I could electrocute myself, so I'm not going to do that. And I'm going to dip this into the water, and nothing happens. Okay, nothing happens here. So what I'm going to do now, I'm going to unplug it. So I'm going to add some NaCl. And what do you know that NaCl will break up into? Na plus and Cl minus. It's not chlorine gas. If it were chlorine gas, then you would actually have what forming inside of here? What would you notice? Bubbles. And we're not seeing any bubbles. So it's not Cl2 gas. So it's just breaking up into Na and Cl. Let's see what happens if I put this in here. Oh, what happened? The light bulb lights, which means what? Electricity is flowing, okay? And so as long as we can get it to flow from one side to the other, then we can get that light bulb to light, right? So if you have an ionic compound, something that dissolves, then you will get that light bulb to light, okay? So what makes it light, what doesn't make it light, we're going to talk a little bit about that when we talk about net ionic equations. So, what basically we're trying to figure out here with net ionic equations is who are the players? Who is playing in the game? Okay, you know, you can go to a game and you can go and you can sit in the stands. What do you call the people that sit in the stands at a football game, at a baseball game, at a basketball game, a hockey game? You call them? Spectators. Perfect. The spectators are the people that come, they sit in the bleachers, they watch the game, they leave the game basically unharmed, unchanged, okay? The players are the people that are going to change. They come in, they play, they may leave with bruises, they may leave a lot happier, they may leave a little bit more upset, but they're going to be changed, they're playing in the game, okay? So what net ionic equations basically are going to tell us is that, and so I want to make sure that you keep that in mind as we work these problems up, because the question is going to be, I don't understand, what is the point of this? And so the point of net ionic equations is to figure out who are the players in the reaction, because sometimes you can react two chemicals together, and some of these ions that form remain unchanged. They come a certain way in the beginning, they leave the same exact way, they are unchanged, okay? And so if they're unchanged, we call them spectators. What we're looking for is who's actually working, who's actually playing in the game. So it says an ionic equation shows what happens to the ions that take part in a chemical reaction. It's hard to visualize what's actually happening to the different chemicals in a reaction. A scientist will write a net ionic equation, or what I'm calling an NIE, to show in detail what's happening to the ions. Okay, so let's first start off by making sure that we understand what it means to be aqueous, AQ. So there are 4 abbreviations that, or I guess symbols that we can use that come in a chemical reaction after a particular substance. And the 4 are S for solid, L for liquid, G for gas, not grams, the G is for gas, and AQ for aqueous, okay? You could have something, all of these in water, okay? They could be in water. But the only one that means that it's dissolving in water and producing, and it's called an electrolyte, where you could actually get electrons to flow across, is aqueous, okay? So you could actually take something and put it in water, and it still remains solid. How? It doesn't what? It doesn't dissolve. But I'm going to tell you even more than that. Because something like sugar, if I were to put sugar in water and try to light the light bulb, it doesn't work. Okay? It would still be, you get no light. Why? What does sugar not do? And the molecule is, you guys remember what sugar is? C6H12O6. That would be glucose, not sucrose, but glucose, that's fine. So C12H22O11. And what does it not do? Because it doesn't break up into ions. Perfect. It doesn't ionize. Molecular compounds do not ionize. They don't form charges. So if you have something like CO2, we're not doing C with a +4 charge and O with a -2 charge. We're not doing that, okay? What we're doing is we're saying that the moleculars, they just share their electrons. So they're actually not charged. They're not positive, negative. And if there isn't a sufficient amount of positive, negative, then you're not going to get that to flow. And you may be thinking, which is a good thought, some of you may be thinking, yeah, but I thought that water does what? Conducts electricity. Okay, it does. Water self-ionizes, but it's not to a great extent, okay? So yeah, you know, you've seen those, all of the huge warnings and the big stickers that are on different things, like in your bathroom, for example, and what does it say on a hairdryer? Keep away from water, okay? So we know that it will conduct, and so if you're on a boat, for example, and lightning starts, and so what do they tell you to do? Get out of the water, okay? And so yes, it will conduct, but it isn't to as great of an extent as something like having an ionic compound. And the reason why is because there are also salts and minerals and things like that in the water too. So, okay. So back to this, when we talk about aqueous, this is really important because this is going to be one of our major things in this, is it refers to a solution of a solid that's been dissolved in water, and it's abbreviated AQ. But it's important that we understand that only aqueous substances will break up into their ions. Okay? So by definition, it's that it's dissolving in water, but back to what I was saying about sugar, sugar won't break up into ions, so we actually would not write AQ after it. We would simply write that it remains as a solid. So even if you're dissolving it in water, it's not breaking up into ions. So the water, in a sense, will separate the ions from one another. A precipitate, this is important that you understand this, it is an insoluble substance that forms and separates from a solution. And so the insoluble, what that means is it does not dissolve. And so you could get precipitates that form in a reaction where you react 2 things together and one of them ends up being a solid. Then that is what you would call your precipitate. Everybody say precipitate. Precipitate. Okay, perfect. And so we already talked about the phase. The first thing we're going to do is we're going to write some equations for solids dissolving in water and what happens to them. So we already did the NaCl. So when you dissolve NaCl into water, so if it starts off as a solid and we dissolve it in water and make it aqueous, then what ends up happening? We said it breaks up into ions. What 2 ions? Perfect. Sodium, so Na+. And then you could write an AQ after, you don't have to, by indicating that it's ionizing would tell you that you're dissolving it in water, okay? That's how you get it to ionize. Plus Cl-, and we're also going to write an AQ after that. Now, if it breaks up and there's more than one atom, or ion is what we're forming here, you want to make sure that you separate the ions. And there's a difference between writing something like, well, let's do this one right here. So it's K2S. And if we break up K2S, what we're going to get is, what 2 ions? K plus and what sulfur's charge? -2. Good. So we're going to get K plus and S2-. Both of these being aqueous. What's wrong? There are two. It's not balanced. Okay. So the question is, do I write K2 or do I write 2K? 2K plus or K2 plus. There's a difference. One of them is wrong and one of them is right. What does it mean if you have a 2 down there as a subscript? They're together. That means they're together. They're connected to each other. Okay? What this means is you have two ions and they're separated from one another. Once it ionizes, they actually can break apart from each other. One takes off in one direction and one takes off in the other direction. So we actually don't want to write it like this. This is the wrong way to write it. This would be the right way to write it. So we're actually going to write 2K plus. Okay? All right, and then let's do one that has a polyatomic ion in it. Remember, polyatomic ions, they carry a charge and they act as one what? One unit. Perfect. It acts as one unit. So when you dissolve it in water, it still will stick together and act as a clique, just like it did before when we did naming. So it's still going to be grouped together as one clique. So what two ions do we have here? Pb. And what's the charge of it? If SO4 is a -2, then what does that make lead's charge? A 4. Perfect. Why 4?
Because when you cross together,
Because it's -2 times 2, so that makes a total of -4. So if the sulfate has -4, then the lead must be, the only one lead must be a +4. So this is Pb with the 4 plus charge. Again, you can write aqueous or not. I'm just going to keep it that way now. And what do you think we need to do with the SO4s? How do we write this? Do we write SO4 2 or 2SO4? 2SO4. Perfect. Because of the same thing that we said before, and the charge is -2, again, you have to include the charge if it's an ion. Okay? And these are all ions. If you say Pb, then we would assume that you mean lead solid. Okay? If you just say Pb, that means that you're assuming that it's solid lead. But if you say Pb with the +4, then that means that it's aqueous, that it's an ion, it's dissolved inside of water. Okay? So again, the SO4, the sulfate, you don't want to write SO4 because that would mean that they are together or connected. Perfect, that they're bonded to each other, and they're not anymore. Once you put it into the water, what ends up happening is, so for example, if I had the K2S going inside of here, what ends up happening is it breaks up and you get K plus, and S2- for every one of them that you have. So if I had 3 of them, then how many Ks would I have? 6. Perfect. I would have 6 Ks and how many S's? 3. Good. Okay. So, all right. So this is a solubility chart. And what the solubility chart basically tells us is what is soluble, what is insoluble. In other words, what will dissolve and what will not. But more specifically, we're not just going to say dissolve because sugar dissolves in water. It breaks off into little tiny molecules so you can no longer see it anymore. But it does not break up into ions. And because it doesn't break up into ions, it will not conduct electricity. So what we're going to look at here is first this word soluble. And what I've got here is aqueous. So this aqueous basically means that it breaks up into ions. Breaks into ions. In other words, positive and negative charges. Cations being positive and anions being negative. If it's written as solid and we're saying it's insoluble, then we can call that the precipitate. Everybody say the word again. Precipitate. Okay? So that would be a precipitate generally. So here I have sugar going into water versus NaCl going into water. This you would actually say is solid, and NaCl you would call aqueous because that will light a light bulb. It will break up into ions where the sugar molecules will not. Okay, so what we're going to do is we're going to first just kind of get an idea of what's going on with this chart so that you know how to use it. Okay, you do not have to memorize it at this level. You just need to make sure that you know how to use it. So at the top here, everything that is above this bolded line here is aqueous. Okay, so that's going to be those are going to be the ones that break up into ions and dissolve. The ones below are all going to be precipitates, meaning that they would be solids if you put them in water. Okay, so what this chart is basically telling us is what happens when you put this stuff in water. Now, sometimes they're ionic compounds, so you're going to be confused because you're like, wait a minute, I thought that lead chloride, I thought that was ionic. It is. It's a metal with a nonmetal. So then how come it's not aqueous? And so the idea would be, what the scientists did when they came up with this chart is they said, does it ionize more than it doesn't ionize? Okay? So depending on whether it has a lot of it breaking up into ions, it will break up into ions. But some of them has such a small amount breaking up into ions that we're going to just call it solid. We're going to say that it's insoluble. Okay? So the first one that's on the list are the alkali ions. Do you remember where the alkali metals are on the periodic table?
Yeah.
All the way where? Far left. The alkali metals are the lithium, the sodium, the potassium, the rubidium. Those are the alkali metals. And anytime that you have a positive ion, an alkali ion, these will all be soluble. So you can have Na anything, you could have Li anything. It could be with nitrate, it could be with sulfate, it could be with sulfide, it could be with phosphate, it could be with nitride. As long as it's an alkali metal, it wants to break up. Okay, it wants to split off. In other words, it will lose its electron, okay, and become positively charged. So the alkali metals are all soluble, meaning they will all be aqueous, okay? NO3, that's called nitrate, and nitrates are all soluble. So are acetates, all soluble. So you could have, now keep in mind that these are negatively charged. I'm not telling you what goes in front. There would be some metal in front of here. So maybe it's magnesium, maybe it's scandium, maybe it's silver, but there would be some metal in front. Remember, you can't have a negative without having a positive, okay? Something had to give it its electron. So it was with something else when it broke off. So there's some positive in front of it. But if it ends in nitrate, it's soluble. If it ends in acetate, it's soluble. I call these the I-clobbers, but it's iodide, chloride, and bromide. And they're all part of the halogen family, okay, which we call halides. These are all soluble, but we've got some exceptions. What do you notice are the exceptions? Because they're pretty much the same in all three. What is this? Silver. There's silver. There's silver. What else? Lead. There's lead. There's lead. There's lead. And do you know what Hg is? Mercury. And mercury. Okay? So if you put silver, lead, or mercury in front of any three of these would all be considered solid, meaning they would precipitate. Okay? So the exceptions are the ones that are going to precipitate, and those would be solid. So now let's take a look at sulfate. Okay? Sulfate is similar to them, and you notice that all sulfates are soluble, but again, what are your exceptions? Silver, lead, and mercury. Silver, lead, and mercury, but now we've got three more. And so I call them, I say it's because, sir. Why? Because, sir. B-A-C-A-N-S-R. Okay, you don't have to memorize them at this point, so that's all. You would just need to be able to use the chart. So again, these are the ones that are solids. These would all be aqueous. Okay? The bottom half of the chart is reversed. This is opposite. These are the ones that are insoluble, and then we're going to talk about the exceptions on this side. Okay? So what are the ones that are mostly insoluble? Sulfides are pretty much all insoluble. What are these called? What's Cl3 negative 2? Carbonates are insoluble, so are phosphates, so are hydroxides, and so are chromates. Okay? And then what you're going to do is you're going to look here at what the exceptions are. What do you notice about every single one of these? 1As, the alkali metals. The reason why is we said that all 1As are soluble. So yeah, those are all going to be exceptions. Okay? If you take a look, the only one that's, for the most part, that's going to be really different is with sulfide, we're also adding the 2As. And what else do you notice about them? What's also the same? What is this called? Ammonium. You can see ammonium in each one of these. Well, there's ammonium on that one, except for hydroxide. Okay? Hydroxide has the, we're now saying because, sir, which is actually reversed, because sir here, these are the solid ones. These happen to be the aqueous ones. So all of these on this side, when it says soluble, these are the ones on this side that are actually aqueous. Okay, so it's reversed. These are the solids that are the exceptions. These are the aqueous ones that are exceptions. Got it? Let's try a couple of them, because what you're going to need to be able to do is, by looking at the chart, you're going to need to be able to say, is it aqueous or is it solid when I put it in water? Okay, ready? On the count of 3, Okay, I'm going to give you a second. I want you to find MgCl2, where it would fit, which one it would fall under on the chart. You're not really looking at the first element unless the first element is what? Positive charge. Which ones are positive? The metals, the metal, the only one you're going to look at are the alkali metals. So that's the only reason why you would look at this. Otherwise, you're looking at the ending, okay? So what I want you to do is I want you to find the Cls. Do you see it? Yeah. Yes? Okay. So on the count of 3, I want you to tell me whether this would be AQ, aqueous, or S, solid. You got it? Yeah. 1, 2, 3. AQ. Very good. Why is it aqueous? It says they are all soluble. Is it one of the exceptions? No. Okay, let's try the next one. FeS. So we're going to try to find sulfides, because Fe is not a 1A, it's not an alkali metal. So let's try to find sulfides, which is right here. Okay, you ready? Okay, AQ or S? 1, 2, 3. S. Good. Why? It says they're all insoluble, which means it's solid. It's not a 1A, iron is not a 1A, iron is not a 2A, and it's not ammonium, so then that must be solid. Let's try the next one. K2CrL4. You could do 2 things on this one. I'm going to give you a hint. You could do 2 things, okay? You could either use that or you could use that. You ready? 1, 2. So AQ or S? 1, 2, 3. Why AQ? You're right. Why AQ? 2 reasons. It's an alkali metal. Perfect. This is an alkali metal. Or if you looked at the chromate, here's chromate down here. What does it say about chromate? They're all insoluble. What? Then how come we said AQ?
With the exception.
It's an exception. Perfect. The 1A, potassium is a 1A, so either ammonium or the 1As. So that's going to be aqueous, okay? Meaning it'll light a light bulb. Okay, let's do the last one, PbCO3-2. So again, you're not looking at the first element unless it's an alkali metal. You're looking at the carbonate. So find carbonate, which is right here. You ready? 1, 2, 3. Solid. S. Perfect. Why? Because they are all insoluble and it's not one of the exceptions. Got it? Okay, so just using the chart, just making sure that you can find which one it matches and then be able to read what it says on whether it's aqueous or solid. All right, so back to the notes. The first thing we're going to do is just explain how we're supposed to write these. So you're going to write a balanced equation, which we know how to do. You're going to write the phases of the substances in parentheses after the substance. Now, typically, your reactants will be given to you. It'll tell you whether it's aqueous because you need to know, was there water involved or was it just a solid? So it'll tell you in the beginning whether it's a gas or if it's aqueous or something like that. So it says for the phase, use your common knowledge and the solubility chart. What I mean by that is, for example, what phase does H2 exist in? Hydrogen. Say it. Gas. What about oxygen? O2. Gas. What about nitrogen? Gas. But if you had something like silver, you would assume that silver is solid. Perfect. Okay? Any of the metals on the periodic table in nature will exist in the solid phase unless they came as an ionic compound and they're dissolved in the water. So if you had AgCl, then yes, it will break up into its ions, Ag plus and Cl minus. But if it's something like just silver, then you're actually just going to write that as silver with no charge. Okay? So remember, they don't lose and gain electrons until they do what? Bond. Perfect. Unless they're bonding, they're not losing and gaining electrons. Okay? So second thing is we're going to write what is called the complete ionic equation. So if it's aqueous and only aqueous, I want you to bubble this word in. If it's aqueous and only aqueous, then, and soluble, then you're going to rewrite the compound as ions in solution. You're going to break it up into its ions. So only if it's aqueous. And then the third thing is, we're going to write our NIE. And the way you write your NIE is you're just going to cancel out your spectators. So get rid of the ones, what are the spectators again? The ones that?
Just watched.
Yeah, they just watched. They came in the beginning, they end, they look exactly the same, they have not changed. It was an ion, it was an ion. It was a gas, it was a gas. Okay. Spectator ions are the ions in the equation that undergo no chemical change during a reaction. They stay exactly the same, and then your NIE should be balanced when you're done. So let's try this. We've got solid zinc reacting with aqueous hydrochloric acid. And so the first thing we're going to do is we're going to write out our equation. So I'm going to write zinc as Zn with no charge. Okay, coming as a solid, so I'm going to write a little S after it because it says solid zinc. And hydrochloric acid, what's the formula for it? HCl, because it's a +1 and a -1, so it's going to be HCl, and it tells you that it's aqueous. So now we've got our arrow, meaning it's dissolved in water. Okay, so what's going to happen is, zinc is sitting on the sideline. Do you remember what kind of reaction this is? And this is our team playing. Single displacement. Awesome. This is a single displacement reaction. So zinc is going to go in, and who's going to come out?
Hydrogen.
H. Perfect. Why?
Because they have the same charge.
Same charge. Awesome. But when hydrogen comes out, it does not come out as H. How does hydrogen come out? H2. And H2 we know is a gas. Perfect. Okay? So you are using your common knowledge now about these. You can look at the periodic table to see if it's red, that means that it's going to be a gas. Plus. Well, so zinc went in and hydrogen came out, so that zinc is now with Cl, but I need to rewrite my charges. So it's Zn with the +2 and Cl with the minus, so when you crisscross, what do you get? ZnCl2. Okay. We don't know on this one. We know that this is in a water solution, so we need to check on our chart. So let's take a look at our solubility chart, and it's ZnCl2. So on here, what am I looking for? Chlorine. Perfect, it's right there. And what does it say? They are all soluble. These are the exceptions. Is it one of the exceptions, zinc? No. So that means it is aqueous. Perfect. So you're going to write an AQ. All right? Second step. Second step is anything that is AQ, we are going to break up. So second step is break up anything that is AQ. You're going to break up into positives and negatives. Okay? You're going to say plus a positive or plus a negative, because you're going to break it up. Everything that's not aqueous, you're just going to rewrite. So this is not aqueous, so I'm just going to rewrite it. Zn solid plus. This says aqueous. What do I do? Break it up. We didn't balance this, by the way. Let's make sure it's balanced. So I've got one H, two H's. So I need a 2 in front of there. That gives me 2 Cl's, 2 Cl's, 1 Zn, 1 Zn. Okay. So this is my only coefficient that's inside of there. All right, so I've got 2 HCl's. What is HCl going to break up into?
Cl minus.
Yep, H plus and
Cl.
Cl minus. But how many of them? 2 of each. Perfect. You have to distribute this. So it's going to be 2H plus, aqueous, plus 2 Cl minus, aqueous. That is this breaking up. Okay? That's the aqueous one breaking up. And you only break up the aqueous ones into ions. Then I have my arrow. Do I break H2 up? Why not? It's a gas. Perfect. It's a gas, and the gas is just going to form bubbles, and then it'll probably just leave your beaker, your flask. Do I break up ZnCl2?
Yeah.
Why?
It's aqueous.
It's aqueous. Perfect. And anytime it says aqueous, that's when you're going to break it up. So on this one, I'm going to break this up, and what is it going to break up into?
Zn.
Zn. And now, if you write it outside, if it's alone written as an ion, and you don't have to worry about this, if you wrote it as +2, it would be fine. It's typically written as 2+ instead, where that inside of the compound is written as +2, but you don't have to worry about it. If you wrote it either way, it would still be fine. So I've got Zn2+. How many zincs are in here? How many zinc ions? Only 1. But how many chlorides are there? 2. So how do I write that? 2 Cl minus. Why not Cl2 minus? Why is that wrong? They're not connected anymore. That means that they're together, and they're not. If CO2 were together and it were alone, it would actually be a gas, and it would float off. It would be toxic to us. It would be something that would be poisonous to us. But it's not. It's 2 Cl minus. Okay, and there's a huge difference. So if you write Cl2 versus 2 Cl, there is a big difference. All right, last step. In my last step, what I'm going to do, I'm going to switch colors here. I want to find out who my spectators are. And what I said was, the spectator looks exactly the same on both sides of the arrow. It is unchanged. Okay? Zinc. Did it change? Why? Yes, it did. Why? It was solid. Now it's aqueous. Now it's an ion. So it changed. Hydrogen. Did it change? Yeah, it was aqueous, and now it's bubbles, and it's a gas. So that's gone. That's one of our players. What about Cl minus? Stays exactly the same. You can either just cross it off, you can just do a slash. I'm just going to do a big S right through it, meaning that it's my spectator. Okay? So I'm just crossing those off. And now what you're going to do for your NIE is just going to rewrite your equation. Everything without the spectator. Zns plus 2H plus yields H2 gas plus Zn, 2 plus aqueous. And if you did it correctly, it is balanced. As long as you did it correctly, it should be balanced, which it is. I've got 1 zinc, 2 H's, and 2 H's. Okay, let's try this again. So this here is called your net ionic equation. And again, what the net ionic equation tells us is who our players are. That's basically what it's telling us, is who are our players in this. Okay? So let's try the next one. We've got aqueous solutions of lead-2 nitrate and sulfuric acid. So they're both going to be aqueous. All right. So lead-2 nitrate, we've got Pb with a +2. And do you remember what nitrate is? NO3. Good. NO3 with a -1 charge. There's 1 mole. So when I crisscross, I get PbNO3 2. And again, they told us it was aqueous. So I don't have to look it up because they said it was aqueous. Plus sulfuric acid. Do you remember what that is? It changes to 8. So it's H+. What is sulfate? SO4 with what charge? -2. So when I crisscross, I get H2SO4. Perfect, which I heard at the beginning. Some people already know it's H2SO4. Again, aqueous. Okay, what kind of reaction is this if I have 2 ionic compounds? Double dating. Perfect. This is double displacement. So it doesn't matter which ones you switch. You can either switch the negatives or you can switch the positives. I'm going to switch my positives. So what's going to happen is my H is going to be here and my lead is going to be there. So what do I get over on that side? H+ is now with what? NO3-. So it's just HNO3. Okay, we're going to look that up in just a second on our solubility chart. Plus, now the Pb is over here. So I'm getting Pb, which had a +2 charge over there, so it still has a +2 charge here, is now with what? SO4, which has what charge? -2. What happens to a +2 and a -2? They cancel out. Okay, let's take a look at our chart. Let's look for HNO3, and let's look for PbSO4. Okay, so the first one is HNO3. What does it say about nitrates? They're all soluble. Perfect. Okay, what about PbSO4? What are we looking at? Sulfates. Good. And what does it say? All soluble.
Exception.
But PbSO4 is an exception. So that makes it what? Solid. Awesome. Okay. So this one is AQ, and this one is solid. Okay? And it doesn't matter whether you write PbSO4 first or HNO3. And then let's balance it. So we've got 1 Pb, 2 NO3s. So I need a 2 in front of there. And then 2 H's, 2 H's, 1 SO4, 1 SO4. We're all set now. All right. Second step. If it's aqueous, we're going to break it up. Okay? You might have to write a little bit smaller so that you can fit all of these on, because you can see that there's one, there's an aqueous one, and there's an aqueous one. Okay? So I'm going to break this up. What does this break up into? Pb with a 2+ charge, and what? How many NO3s? 2. Do I write it in for the 2 in front or the 2 at the end?
2 at the front.
In front. Good, because they're no longer what?
Bonded.
They're no longer together, they're no longer bonded. So I'm going to write Pb 2+ plus 2 NO3-. Notice that I didn't write the AQ in. As long as you write it as an ion, you do not need to write the AQ in. Okay? It's assumed that if it's an ion, that it was aqueous in solution. Plus, what do I do here with this aqueous one? Do I write H2? 2H. Good. 2H plus. Now this is a polyatomic ion, so it's going to stay together. So I'm going to do SO4 with a -2 charge. Now I have my arrow. Do I break up HNO3?
Yeah.
Yes. Now it has 1 H and 1 NO3-, but there are 2 of them in front. So how many H's do I have now? 2 H plus. And then don't forget to distribute, plus how many NO3-? 2. Perfect. 2 NO3-. Do I break up the PbSO4?
No.
No! Awesome. Why not? It's solid. Okay, if it's solid, do not break it up. It's just going to be PbSO4 solid. The last step is my favorite. This is finding who the spectator is. So can you see, is there anything that looks exactly the same on both sides? In other words, it did not change phase. It was an ion. It is an ion. Call it off if you see one. Perfect. I see the hydrogen. I heard hydrogen. So that looks exactly the same on both sides. So this one here with this one here. And then I heard another one.
Nitrate.
Perfect. The NO3-, the nitrate, also looks exactly the same. Okay? So what are we left with? We're going to rewrite what we're left with. And what we're left with is Pb2 plus SO4 2 minus yields PbSO4 solid. And again, this is what we call our NIE. Feel like you got it?
Yeah.
Let's try one more together. Let's see how we do. All right, so in this case here, we've got aqueous solutions of silver nitrate and sodium chloride. So silver nitrate is Ag with a plus charge. We know nitrate, we did that before, NO3 with a negative one. So what happens to a positive and a negative? They cancel out. And this says is aqueous, and sodium chloride. Sodium's Na with a plus charge, and chloride is Cl with a minus charge. Arrow. What kind of reaction is this one again? Double dating again, double displacement again, which means I'm just going to switch my two positives. So if I switch, the Na comes over to the other side. I get Na with a +1 and NO3 with a -1. Again, a positive and a negative just cancel out. And now my Ag is going to come here, and I'm going to get Ag plus Cl minus. We need to check to see. Oh, sorry, NaCl we know is aqueous. It told us anyway. Let's look on our chart for NaNO3, and let's look at our chart for AgCl. Okay? What do you think for the first one? NaNO3.
Soluble.
Soluble. Why? Two reasons.
There's no exception.
Yep. Alkalis and nitrates are all soluble. What about AgCl? It's an exception. It's solid. Why? You're looking at chloride, and what does it say? All are soluble except AgCl. Okay, so we're going to come back here, and we're going to write that this one is a solid, but this one is aqueous. Okay, and again, we're just going to start breaking up the ones that are aqueous. So if it says AQ, break it up. So balancing, 1 Ag, 1 Ag, 1 NO3, 1 NO3, 1 Na, 1 Na, 1 Cl, 1 Cl, it's already balanced. So I've got Ag plus what? NO3 minus, good. Again, the polyatomic ions stay together as a unit. What does NaCl break up into? Na plus and Cl minus. Again, if you do not include your charges, it's wrong, okay? Because then you're assuming that it's solid sodium, and it's not. What does NaNO3 break up into? Na plus and NO3 minus. And you break up AgCl. No, it's solid, so keep it together. All right, and do you see any spectators?
Sodium.
Good, the Na is a spectator, very good. Any NO3 minus is a spectator, perfect. And so now we're just going to rewrite our NIE, which is everything left over. So these are our players. Ag plus Cl minus yields AgCl.